All right, welcome to CAM 395, Experiment 4, which is X-ray diffraction and fluorescence. So in this video, we will learn how to process the data that we obtain from the X-ray diffraction part. Namely, we will look at the angle of diffraction. We will process them such that we got the lattice constant and we know the structure of the sample. So here we will be looking at how we can play using Microsoft Excel, which is a very famous spreadsheet program. And we will learn some tricks that will help you organize your data nicely so you can present it and in a clear way. Okay, so for the purpose of this tutorial, I have compiled a set of picks, and I will assume that we know that our sample is a calcium metal from the X-ray fluorescence, let's say. So in addition, I have also compiled several relevant data that we will later need to verify that our pick assignment is correct and our analysis is proper. And also in all of the calculations, we will need the wavelength of the X-ray instrument, which you can find in the handout. In addition, I have also taken the liberty to copy and paste several equations from the handout that we will actually need to process the information. Okay, so here I will assume that you have already went through the lecture about indexing, and if you have not, I highly recommend that you do so. In any case, let's start without further ado. So let's say I've made my X-ray graph, and this is the set of data that I have, and now we need to process it. So the first thing that you want to do is, of course, to have a header, because we will be treating this like a table. And we want to make sure that any person who opened your spreadsheet, including yourself, can look at it and remember or can understand what is going on in the spreadsheet. So it is not a bad idea to always include a header. So if you remember, in your tutorials or in your data, this is the 2 theta, and so I will regard it as 2 theta, or you can also use theta, as long as it's clear. Right. So I will do it this way just to save time, but you can always play it fancy by using insert, symbols, and then find your Greek character or the other characters that you need. Okay, so this is 2 theta in degrees. Now, before we proceed, the formulas we need for indexing is given here, where we need to take the sine theta squared. So let's do it one step at a time. You can always do it in one shot, but doing it one step at a time will minimize the risk of getting an error in the calculation. Okay, so first, we definitely need to convert 2 theta to theta, which is simply just that divided by 2. Okay, and you can always copy it down. And now the quirky thing about Excel is that the sine or any trigonometric function will take units of radians. So let's do the conversion in a separate column just to make sure we don't do anything weird. To do that, you can simply type radians and put the angle in. And that will give you all the angle that you need in radians. Okay. Now, for the sake of presentation, you can always decrease the number of decimal places that you're showing, so it looks neat. Not necessary, but again, for a presentation, it's always nice to do so. Okay, so now let's take the sine of the angle, because we already have it in radians, so it's as easy as saying sine of the angle in radians. All right. So you might not get this formatted nicely at the beginning. I have set up my spreadsheet so such that I have this for decimal places. So you can play around with that. Okay. So now next information we need is sine squared of the theta, which is simply this number squared. Okay. All right. Now we're ready to do the indexing, and if you remember, so the indexing can be done by using this equation from the handout, where this whole thing in parentheses is a constant a, and we will guess the value of a, and we will see if the rest of the angles will give us an integer value by using the same number for a. So here I will put a value, and what I like to do, just to make sure I don't miss anything, is I like to index all possible cases. So in this case, we already said in the handout that all of the structures of the sample will be that of a cube. So we will give you either primitive cubic, body-centered cubic, and or face-centered cubic, nothing else. So what we need to do, we know that from the table 1 in your handout that the very first pick will give an m-squared value of 1 for primitive cubic, 2 for body-centered, and 3 for face-centered. Okay. Now using this, we can get the a value for each of the cases, where the a value for a primitive cubic is simply this divided by that. But now, just to make sure I can copy this nicely, I will lock this by pressing F4, or put the dollar sign on the cell that I want to lock. So now, if I copy this to the right, I will always lock the E2, but I can change whatever that I do not lock. Okay, so now we have the A value that we can use to guess, and we will start indexing each of the case. So let's start with this. So we see that the m square is given by sine square divided by a. So sine square divided by a. So now, just to show you how powerful locking can be, here we know that if I copy to the right, I want this part to stay in column E. So I will lock just the column E, but the row will be free. When I'm going down, I want to make this stay at row 10, but I can change the column, whether F, G, or H. So I will just lock the row 10. By doing that, I will always get the correct value. For example, here, it's this divided by this, so that's correct. It's one way to check it. It's this one divided by this, so it's correct. All right, so now once you're doing your indexing, again, initially when you're doing it, if I just say the formatting is general, this is how it would look like. But I suggest, because we want to check whether we have integer values, let's keep it close to an integer. So let's reduce the number of decimal places that you are showing. Okay, so here we can immediately see that the primitive cubic doesn't give me an integer. Body-centered cubic, nope. And face-centered, looks like we got a winner. So it's not a bad idea to just mark it differently. You can use highlights or whatever. Just make it bold or italic. But it's always a good idea to mark something that you want to work with so you don't forget. Now, before we proceed, it's also not a bad idea to check against the value of m squared in your handout. And if you check the table, you will see that we have a pretty close agreement. But here, between 16 and 20, we are actually missing an m-square value of 19. So if you experience that while you're analyzing your data, what you need to do is go back to your X-ray diffraction data and see whether there is any small peak located between these two angles, and add that information here and see if it gives you 19. Or maybe you miss something after that, but the same principle applies. You want to include as many picks as possible in your series. Okay. All right. So now let's move forward. So we have indexed all the picks. We know it's an FCC structure. We know the m-square values. So now what remains for us is to determine the spacing of the planes, and then from there we can get the lattice constant given here. Now, before we actually do that though, we need to make sure that we actually use the integer values for the m-square, because if not, then your calculation will result in the exact same value for the lattice constant, and your standard deviation will be 0. So that's not what we want. So now let's make sure we have the integer values. Of course, you can always type it manually, but since we are using Excel, you can also use the formula round, and we can round this number to 0 decimal place. And if I format it as general and copy it down, now it will give me integer values. Now, why I like doing everything using the formulas is because let's say you did found the pick that gives you 19 between 16 and 20. Right? If you have it like this, you can just copy it down and everything will adjust to whatever this value here is. But if you put these integers manually, then you have to redo at least this part of your table and all the subsequent calculation, which is can be painful if you're dealing with a massive amount of data. So if you can use the formula and if you're comfortable with it, do it by all means. Okay, now we have the m-squared. So before we proceed, we notice that we will need to convert to a using the square root of m-squared, which is m. So let's take care of that now. Okay. All right. Again, I will just use number just for cleanness. Okay, so now I will calculate first the spacing here using this formula. So calculate d, which I will put in angstrom. So in the handout, I believe the wavelength used in the X-ray is given in picometers, but you can also use angstrom. But make sure that you understand and remember which unit you're using. Okay. I like angstrom, so I will use angstrom, and I will use it consistently. Okay. So now here we need to calculate d, which is given by lambda divided by 2 times sine theta. Okay. Right. So let's do that. And of course, sine theta changes, but lambda is a constant, so it should change once we go here. And if you index everything properly, then your spacing between the planes should decrease as you go with increasing Miller indices. Okay. And now my lattice constant, finally, is related to the using this very simple formula, and just by rearranging it, you can see that A equals D times M. So it's going to be V times M. All right. So that's the lattice constant that we have from our experiment. Okay. So at this point, it's not a bad idea to also calculate the average lattice constant that you get in angstrom, which you can calculate using average. And just select the range. And since the literature value here have 3 decimal points, not a bad idea to show 3 decimal points as well. Or in fact, remember, you can always check how many significant figures you have and do the propagation and see how many significant figures you should report. Just for the sake of clarity, I will use 3 decimal places, and we can see that we obtained a pretty close agreement with experiment. Okay, so now remember, you will also have to calculate your standard deviation, or not standard deviation, the error with 95% confidence limit. So let's do that as well. So here I will need several data first. So number of data points is going to be count this thing. Of course, if there are only 3 picks, you can always say it's 3, but I'm too lazy to calculate. And again, you can always use formula in Excel. Gives me 7 data points because we are calculating the average. So the degree of freedom is going to be the number of data points minus 1. Now I also need the t value of 95%, and degree of freedom is 6. So I can also calculate it using TINV. Now the probability is 1 minus 95%, or 1 minus 0.95. So it's going to be 0.05, and the degree of freedom is given here. And now we need also to calculate standard deviation, which is given by STDEF of this data. All right. So now, after all this painful formula typing, we can check the error with 95% confidence. Of course, it has the same unit as the average itself. It's given by the t-value multiplying standard deviation over square root of the number of the data points. Okay, if you don't remember, go to the error analysis lecture and it should be there. Voila. So remember, when you report error, you want to follow the decimal place of the average value. So here, I will report my lattice constant as 5.593 plus minus 0.003 angstrom. And unfortunately, my literature value is a little bit out of the range, but it's not a problem for me now. You can always discuss what that means in the lab report. Okay, so now it looks like, let's also format this so we know it's a good value. We know those are the values that we want. Okay, so now we know that the calcium metal crystallizes in an FCC structure. We know that we have a pretty good agreement in the lattice constant, but we need to another step to verify that we get the right structure. Okay, so to do that, I will do a little bit calculation. Of course, uh, you know, you want to make sure that people can understand what we are trying to do. So I will do it down here. So we'll not mess around with the space up here. So you can always say this is verification using number of unit formula units per unit cell. Okay, so what we will do here is we will try to calculate how many formula units, which in this case it's a calcium atom, is present per unit cell. Right. So from the lecture, you should remember that in a primitive cubic lattice, you have one formula unit per unit cell. In a body-centered, you have two, and in a face-centered, you have four. So we'll try to calculate and see whether there is indeed four calcium atoms inside the unit cell. So to do that, we need several information, namely the density of the calcium metal, and of course, its atomic mass, or if you have the binary salt, it's a molar mass. Okay, so first, oops. Okay, so first, from the density, I want to calculate the number of moles per centimeter cubed. Okay, now to do that, I will need to divide my density in grams per centimeter cube by its atomic mass. Okay, and if you do the conversion with the unit, you will also see that this is going to be mole per centimeter cube. Okay, so now I know that there are 0.03 moles of calcium atom in a centimeter cube. Now here I will flip it. So now I will know the volume of a mole of calcium atoms. Let's do this. Too much. Okay. So which is simply 1 over the number of moles per centimeter cube. Right. So if I convert it, it's going to be centimeter cube per mole. So we know that 1 mole of calcium atoms occupy 25.86 centimeter cube. And now I will calculate the volume of a single calcium atom. Right? So to do that, I will actually need the Avogadro's number. So we'll divide this by the Avogadro's number, which is 6.022 times 10 to the 23rd. Okay. Now that's centimeter cube. Okay. So as you can see, and as you can imagine, of course, a single calcium atom has a very, very small volume, which you should be able to get. So if your calculation up until this point produces something a little bit big or 10 to the 23, you know that you're introducing some error when you're doing the calculation. Okay, so now I will also take our lattice constant, but I will convert it to centimeter. Because we want now to calculate the volume of the unit cell. Okay, so now we need to convert this to angstrom, from angstrom to centimeter. So it's going to be divided by 10 to the 8. Or you can also say times 10 to the negative 8. Okay. Right, so that's in centimeter. And now I will calculate volume of unit cell. Okay, because it's a cube, so it's simply this cube. And the unit is centimeter cube. Okay, now I know the volume of a single calcium atom. I know the volume of a unit cell. So the number of calcium atoms per unit cell, as you can guess already, is given by the volume of the unit cell divided by the volume of a single calcium atom. And it gives me something that is close to 4. And of course, we can always make this show less number. But now we see that there are 4.074 calcium atoms per unit cell. And we know that for FCC, we need 4 calcium atoms per unit cell. So that's really close, and that gives us the confirmation that we did the analysis properly. So one last step is let's round this number. So rounded number of calcium atoms per unit cell. Okay. So just to make it wider, again. So remember, if you want to round it to integers, you round the number to 0 decimal place. And okay, we'll still have some decimal places, but if you say general, it's going to give you an integer. And that's another information that you will have to put in the discussion. Okay, so to summarize, we have processed the data, we have put data, we do all the conversions needed for Excel to be able to work with it. We did all the indexing, guess the A value, and then do the rest of the angles by guessing that this is 1, 2, and 3. We obtained an FCC structure. We calculate the spacing of the planes, and we calculate the lattice constants. And we obtain the average value of the lattice constants and its error with 95% confidence. And then an additional verification was performed by calculating how many atoms are there inside a unit cell. And we got a pretty good agreement with what an FCC cubic structure should have. So we know that our analysis is correct. So that's it for this video. Have fun and play around with your Excel.